Hey everyone, it's me, Mr. Younger. I'm here to work another center of mass example. This specific example is me using a continuous object, specifically a framing square, my personal framing square. I actually measured it. However, my framing square is made out of aluminum, and this one I actually said was made out of steel because it turns out the manufacturer that made mine makes another version that is made out of steel. So, anyways, it is a continuous body, but it's very geometric. It's easily dissected into individual parts that have a very simple geometry. And in fact, I could make it into two rectangles and one square, or I could just make it into two rectangles and specifically rectangular solids, because obviously we don't have two-dimensional objects in reality, but it is very thin. It's on the order of like an eighth of an inch thick. So, we're going to treat it like it's sort of two-dimensional, even though we are making use of the three dimensions. As I said, it is continuous, but because of its highly geometric configuration, it's really easy to break it up into separate parts. And I'm going to use that to calculate it as if it is a discrete body. So let me go ahead and share my computer or my iPad screen with you guys so that you can see what kind of work I'm doing here. I've got a lot of it already drawn out. In fact, I had the whole thing drawn out, but I somehow erased it by mistake. So, anyways, we're going to redo it again. So this is the initial problem. You can see it now. You're looking at the iPad screen now. This is a framing square. In fact, I've got it drawn just as it is, sort of in two dimensions. Technically, it actually has a thickness from what you see here in black. In fact, the thickness goes in towards the page, and it's about, like I said, about an eighth of an inch thick. So I said the figure to the left represents a 0.31 centimeter thick framing square used by builders. It is made of steel, but that is not necessary to know to solve this problem. Use and state any assumptions that are necessary to compute the center of mass of this tool. So that's what we're trying to do. We're trying to calculate the center of mass of this. Again, this is a single continuous body. So in principle, I could integrate. I just have to make, lines to represent the boundaries of the square. But in this case, because it is so reminiscent of squares and rectangular solids, I'm going to use the general discrete formula, which is basically the x center of mass equals the summation of m sub I x sub I over the summation of m sub I. And then the y center of mass is equal to the summation of m sub I y sub I over the summation of m sub I. Again, when you're using that formula, if the m sub I are not point masses, then you have to find the center of mass of each of the objects, M1, M2, M3, so on and so forth. So we're going to be doing that as well. Let me go ahead and flip to the next page where I start to write out some of the assumptions and other stuff. So I flip to the next page, and what I've now included is a three-dimensional representation of the framing square. I've added a little bit of thickness, as you can see by the red markers, and the blue writing 0.31 centimeters thick. I've went ahead and labeled the 60.96 centimeters a length capital L. I've labeled the 5.02 centimeters a width capital W. I've labeled the narrower length horizontal as lowercase l equals 40.64 centimeters. And I've represented the vertical thickness of that arm that sticks out to the right as 3.81 centimeters is equal to omega, or you could call that a lowercase w, either one. So I'll be referring to those figures later when I start to talk about the geometry of it. You can even see it down at the bottom. And first, I will label the data given. So that's what I said in the solution. Assumptions. The mass of this framing square is uniformly distributed throughout the square's volume. In short, this means that of this every cubic millimeter of the square has the same mass as every other one, and that a 2 cubic millimeter sample would weigh twice as much as the 1 cubic meter chunk. So, what I'm saying there is it has a uniform density, and that density basically is a constant. And in fact, if you double the size of it because the density stays a constant, that's equivalent to doubling the mass and doubling the volume. So if you take the idea that density equals mass over volume, then doubling the mass and doubling the volume gives you back the same density. So I said, in short, this basically means that mass of 1 cubic millimeter is a constant. Also, a mass of 2 cubic millimeters is two times the mass of 1 cubic millimeter. Or the easiest way of saying that is rho, the volume density that we've talked about before, which is normally defined as the differential change in mass with respect to volume, dmdv, is equal to a constant. So my other assumption, another assumption I'm going to make is assumption two. Assume that the total mass of the square is m, and its volume density rho is given by rho equals mass over volume. The mass, of course, is just going to be capital M. So I'm going to pretend like I know that. Hopefully, we think it's going to actually cancel out. I mean, I know it's going to, but that's what I'm trying. That's what I'm trying to show you guys is that the mass will actually cancel out, so you won't actually need it. And using the formula density equals mass over volume, I get equal mass, capital M, divided by the volume. So what I've done is I divided the volume up into two separate rectangular solids. One rectangular solid is this guy right here. And you see that guy has a height L, a width W, and a thickness T. So that's why I write L times W times T. And then this part, notice that L, lowercase l, goes all the way to there. I really only want it to go to here, and this width is capital W. So the width of this rectangle from here to here, this length really is L minus W. And then, of course, this width is omega or lowercase w. So you can see the area is L minus W times omega, and then I just multiply it by the thickness T. So that really is the formula for the density in terms of nothing but symbols, and we can put the numbers in as we need them. I should also say that, the formula requires x center of mass is equal to m1 x1 plus m2 x2 plus m3 x3, so on and so forth, where those x's, if they're not point particles, they have to be centers of mass, and specifically the x1 has to be the abscissa of the center of mass, and the y1 has to be the ordinate of the center of mass. So we really need a coordinate system. So I have chosen to imagine the framing square as being made up of two rectangular solids. One rectangle is W wide, has a height capital L and a thickness T. The other has a width, which evidently I've left off my cross on my T, has a width of L minus W, a height of omega, and a thickness T. And in three, assume that we have a coordinate system whose origin is at the top left corner. So I'm saying the origin is going to be right here. The positive x-axis runs to the right along this side. That's going to be my x-axis. And the positive y-axis runs along this side and points downward. So that's what I'm going on. I'm going to go ahead and I've already actually drawn that coordinate system, and I'm going to show it to you on the next page. And you can see right there, I have the coordinate system drawn. Now, I'm treating it all like it's two-dimensional, but obviously the thickness shows that it's three-dimensional. I would just want to tell you that trivially, we can trivially determine the center of mass in the z direction because obviously it'll be half of the thickness. From a z standpoint, this thing is just a thickness t. Therefore, we're going to make it a thickness of 1/2 of t would be where the center of mass is, and half of t is 0.1505 centimeters. So that's what I've listed here as well. So it will be completely sufficient for us to talk about the x center of mass and the y center of mass without regards to the z center of mass. Now that we have all this, we can go ahead and start trying to solve the specific problem. So what I know is that M1 is going to be basically the density, because density equals mass over volume, times the volume of rectangle 1, and we already found that the volume of rectangle 1, which I'm treating as this guy. So that rectangle is rectangle 1. So we see that one has a volume given by L times W times T. So if I multiply the density times L times W times T, then I'll have the mass of M1. Now, additionally, I need X1, which is the center of mass of of the rectangle 1. Well, the center of mass in the X direction is just half the width of the rectangle. So, for instance, we're talking about this rectangle right here, and again, we're ignoring the Z dimension, which, by the way, goes into the board. That's the positive Z direction, is into the board. But anyways, we're looking at this rectangle, and clearly right down the middle at W over 2 equals X is actually the center of mass. So X1 should be equal to specifically W over 2. And that's specifically because the y-axis is right here to the left of the left rectangle, and we only need to go half the way over. Now, the other rectangle is going to have a mass M2. Now, that mass is going to be the density again times the volume. But this rectangle, by the way, only goes over to here because it is, if I went all the way to here, it would include part of the rectangle that I've already done. So I really only want to include this part. And of course, this width from here to here is the L minus W that we talked about. The center of mass of it, by the way, is at L minus W over 2, at least in the X direction. In the Y direction, that's a different story. And in fact, I'm going to go ahead and put the M2 on the next line since I hadn't done the Y one yet. So M2 is going to be rho. Now, in this case, it's going to be the volume is L minus W times lowercase w, that's the height, times t. And then the x1 in this case is going to be w. I've got to go all the way across the first rectangle. So I've got to go at least to w, and then I'm going to take half of what's left. So x1 is going to be w plus L minus W over 2, and that's the center of mass for that one. That's just the center of mass in the x direction. Now, the center of mass in the y direction for the leftmost rectangle, remember that rectangle goes from here to here. So what I want to do is go down half of L. Notice the x-axis is right here, so that's y equals 0. Dead center would be L over 2. So I'm going to say y1 is equal to L over 2. That's easy peasy. Now, I also have to figure out what y1 is for the other rectangle. This rectangle, remember, is this guy. Now, that center of mass obviously would be at 1/2 of this thickness. So halfway between this line and this line is basically y equals positive L over 2. So I'm going to say y is equal to, or should be not L over 2, positive lowercase w slash omega, whichever you want to call it, omega over 2. So there's the center of mass of that. Now that I have that, I can go ahead and write that X center of mass, and I'm keeping these symbols for a reason. You're going to see there's a lot of cancellations. That's the whole purpose of me keeping all these symbols for so long. So the X center of mass is going to be equal to M1 X1 plus M2 X2 over M1 plus M2, which is going to equal M1, of course, is going to be rho L W T. And then X1 is going to be W over 2. And then M2 is going to be rho times L minus W times omega. This one's a W, that one's an omega, times T. And that is the whole mass. Now I've got to multiply it by X1, or excuse me, X2. That should be a 2 there. And that quantity will be W plus L minus W over 2, like that. And then all of this will be divided by rho L W T plus rho parentheses L minus W omega T, like that. And the reason why I wrote all this symbolically is you can see that here's rho as a common term to both of them, and here's rho as a common term to both of them. So, in fact, the answer that I'm going to get is going to be independent of the density. So it doesn't matter if this was steel or aluminum, I'd still get the same result. Not only that, I can see that I have a common factor of T. So that T is there. That T is also in this term, and that T is in this term, and that T is in this term. And in fact, I can cancel out omega, or excuse me, rho and T, the product of them. And that rho times T, notice it would have units of, rho has units of kilograms per cubic meter, and T would have units of meters. So if you multiply rho times T, it'd be kilograms per meter. And in fact, what that is the sigma, the density, the area density that we talked about. So I'm going to write right here just as a little reminder and as an extra learning chance for you in case you didn't understand my terminology that dm is equal to lambda dl, or it's equal to sigma dA, or it's equal to rho dV. I will tell you now that rho times T is the sigma. And you've now seen an example of how to actually calculate the mass, or excuse me, the rho, by taking the mass and dividing it by the volume. So hopefully that note that I just gave you plus this experience will help you with all of that. Now we can actually just put in all these numbers and do our calculation. And other cancellations might actually pop in, but that doesn't matter too terribly much. What we really care about is getting the result right now. So the L we know is, and I'll just keep it in centimeters. I could convert it to meters, but all right. So I can go ahead and plug these numbers in. I'm going to keep it all in terms of centimeters because it's really easy. So L is going to be 60.96. I've got the units written up there, so there's no need to actually show them again. And then the W is equal to 5.02, and those are both centimeters, of course. And the T has disappeared, but now I've got to multiply it by the W over 2, and the W over 2 should be 2.505. So 2 point, well, actually, let's go ahead and write it in as W over 2 so that no one will get any confusion as to what it is. So it's 5.02 divided by 2. That is the X center of mass for the leftmost rectangle. Now I've got to do the same thing for the second rectangle, which is the one whose width is L minus W. In this case, I'm doing L minus W, which is 40.64, minus W, which is 5.02. So that's my L minus W. Now I've got to multiply that by my omega, and my omega is 3.81. Again, that's centimeters as well. So I got centimeters squared times then the x, which is another centimeter. So I'm going to have centimeters cubed over basically centimeters squared in the bottom, which you'll see in a second. So now that's the L minus W times the omega. Now I've got to take W plus L minus W over 2. Well, W is 5.02, and L minus W is basically 40.64 minus 5.02 divided by 2. And then all of this has to be divided by what's left in the bottom, which you see is 60.96 for the L, 5.02 for the capital W, plus 40.64 minus 5.02 for the L minus W, times 3.81 for the omega, and that's it. Notice again, like I said, each of these terms here have units of centimeters cubed. And then these terms have units of centimeters squared. So ultimately, the result should come out in centimeters. That being said, I'm going to steal this by using my little lasso tool and copying it over to the next page. I'll say copy. And now I'm going to say paste over on this side. We have that. And this, like I said, is the X center of mass. So I can go on and write this as follows. 60.96 times 5.02. And now I'm going to do some of the simple computations like division and subtraction. 5.02 divided by 2. I've already told you that's 2.505. And, oh, actually, no, that's right. I thought it was 5.01. So this is 5.02, so this would be 2.51 for the 5.02 over 2. The 40.64 minus 5.02 gives me 35.62. So that's going to be 35.62, again, centimeters, times 3.81, again, centimeters. And then if I take the 40.64, which is 35.62, and I divide that by 2, that gives me 17.81, and then I can add that to 5.02, and that gives me 22.83. Okay, so that is the 5.02 plus the 40.64 minus 5.02 over 2. That's all of that is in that one little pair of parentheses there. And then down here, I can do the multiplication again. I'm going to do 60.96 times 5.02, and that's 4 sig figs times 3 sig figs. So this gives me 306.02. That gives me 2 extra sig figs for that one. Now this other one is 40.64 minus 5.02. I'll tell you again, that's 35.62. The 35.62 is going to be multiplied by 3.81, so times 3.81. That's 3 sig figs times 4 sig figs. That gives me 135.71. And that's basically the simple arithmetic part of X center of mass. So now all I have to do is go ahead and do all this multiplication. So 60.96 times 5.02 times 2.51. That should be cubic centimeters, and I'll write it this time. And that's 4 sig figs times 3 sig figs times 3 sig figs. So that gives me 3 sig figs. So that's going to be 768.11. And that's centimeters cubed. Plus, now I'm taking 35.62 times 3.81 times 22.83. And again, this is 3 sig figs times 4 sig figs times 4 sig figs. So that should give me 3 sig figs total. And in this case, it's a much bigger number. Let's see, 35.62 times 3.81 times 22.83. This gives me 3098.3, but it's only supposed to have 3 sig figs, so these two are not significant figures. Now I'm going to say 306.02. That's only good to the ones place, and I'm adding it to 309, or excuse me, adding it to 135. Adding it to 135.71. So again, they're only good to the nearest whole number, and that gives me 441.73. The 7 and the 3 are not sig figs, and this is centimeters squared, is what that came out to be. So I'm finally able to take 768.11 plus 3098.3. That's only good to the tens place because of the 3098.3. So when I add these two, that gives me 3,866.4, but the 6 and the 4 are not significant figures. And that divided by 441.73. And this whole thing just comes out in centimeters. So finally, I can say X center of mass for this one is 3866.41 divided by 441.73. And that is 3 sig figs divided by 3 sig figs. So this gives me 8.75. And then 2, 9 are not significant, but I included them anyways. So that's the X center of mass for this. And notice we were able to do that without the density, without even knowing what material it is. And in fact, I don't think I even ultimately used the thickness 0.31 anywhere. Nope, other than to compute the Z center of mass. So we've got that. Now I'm going to take my Y center of mass formula and use that. So I thought I had already copied it over there, but I hadn't. So now I'm going to go ahead and do the Y center of mass. Y center of mass would equal M1 X1 plus M1 Y1 plus M2 Y2 divided by M1 plus M2. And again, we can make a lot of cancellations here. Let's see if I did do that. No, I didn't do the cancellations yet, but we can go ahead and write out exactly what they are. So the M1 is going to be the density rho, and then the rectangle one has a height of L and a width of W and a thickness T. So that's M1. The Y1, however, is half of the L downward. So the Y1, remember, is capital L over 2. It's downward. That happens to be the positive Y direction, so we're good on that. So I'm going to put just L over 2 there for Y1. Now the mass 2 is going to be the density of the square again, which is just plain rho, times the area and then times the thickness of the other rectangle. Well, the other rectangle has a width that is L minus capital W, and then it has a height that is omega, and then it has a thickness that is T. So I'm going to put this in square brackets to represent M2. And now the center of mass of this one is, remember, I've got to go over W and then add to it L minus W over 2. So the center of mass in this case is going to be W plus L minus W over 2. And then all of this has to be divided by the two masses, which again will be rho LWT plus rho L minus W omega T, like that. And we can see again that rho is common to all the terms in the top and bottom, so we can cancel that out. We can also see that T is common to all the terms on the top and bottom, so we can cancel that out. And remember, T is basically the same, or excuse me, the rho times T is the same thing as sigma. So now I can just begin by putting in the numbers. I'm going to do it just like we did before. So the L is 60.96 centimeters. The W is 5.02 centimeters. And the T is canceled out. The L over 2, on the other hand, is 60.96. I'm going to not take as many steps this time. 60.96 divided by 2 is going to be 30.48. So you see that's another centimeter. So I do get centimeters cubed up here. Now I'm going to take the L minus W, which was 40.64 minus 5.02, and that's going to give me 35.62 centimeters for the L minus W. And then the omega is 3.81, like that. And now I've got to put the y center of mass, which is W plus L minus W over 2. So I'm going to take the L minus W over 2 first. This is L minus W is 40.64 minus 5.02, and that gives me 35.62. I divide that by 2. That gives me 17.81, and I'll go ahead and take one extra step. This is going to be 5.02 centimeters plus 17.81 centimeters. So you can see again, I do have centimeters cubed in the numerator. Now all I have to do is write the mass part of this that's left. In other words, leave out the L over 2, leave out the W plus L minus W over 2. That's going to give me basically the 60.96 times the 5.02 plus the 35.62 times the 3.81. And you can see that centimeters squared in the bottom. So I got centimeters cubed over centimeters squared. That should be pretty good. 60.96 times 5.02 times 30.48 gives me 9,327.5. Now, in this case, that was 3 sig figs times 4 sig figs times 4 sig figs. So those last two are not significant. That means it's only good to the tens place. Now I have to add to that the same multiplication I did, or that I showed written here. That's 35.62 times 3.81 times. Now I'm going to take parentheses 17.81 plus 5.02, and that should give me basically 4 sig figs again. And this gives me 3,098.3. And you can see again that's 3 sig figs times 4 sig figs times 4 sig figs. So the 8 and the 3 are not significant figures. So I'm just going to put all the units up here now that we know them. And then down at the bottom, 60.96 times 5.02 is equal to 306.02. And that was 3 sig figs times 4 sig figs. So We're basically just getting 3 sig figs there. And then I'm adding to that the 35.62 times 3.81, and that gives me 135.71. And again, that's 3 sig figs times 4 sig figs. So that's giving me 3 sig figs, which means it's only good to the ones place. And all of this is just in centimeters squared. So you can see the final result should be centimeters cubed. Now, if I add the 9327.5 and the 3098.3, that's only good to the tens place, but I get 12,425.8. But the ones place and the tenths th does not count. So that's what my numerator is. And now 306.02 plus 135.71, that's only good to the nearest whole number. So that's 441.73. And the 7 and the 3 are not sig figs. And the total answer, since the centimeters squared cancel out, leaving just a centimeter on top, should be that. So I'm going to take 12425.8 and I'm going to divide that by 441.73. And this gives me, oops, this gives me the y center of a mass is 28.12. And in this case, I had 4 sig figs divided by 3, so that's really only 3 sig figs. And the digit after the 2 should rightfully be a 9, but that's followed by an 8, so I'm going to write this as 30. So scratch that out and write this as 30, and neither one of those are sig figs. So the y center of mass for this object is 28.13 centimeters, but really we can only count 28.1 centimeters, and we can only count 8.75 centimeters for the X center of mass. So I hope that helps you see some of the tricks that you can pull whenever you encounter a variable that you don't know the quantity that represents it. Then treat it as a variable, hoping that later out on it's going to cancel out. So you just give it a symbol like capital M or lowercase x or q or alpha or whatever. And if you get a mathematical chance to cancel one of those terms out, then you know you really didn't need it. If it doesn't cancel out, you either made a mistake or they made a mistake in making up the problem. So in this case, we do actually find that the center of mass should be at these positions. So let's go ahead and look at the actual. Let's start from this one. I'm going to copy this page real quick. So I'll have this drawing. And specifically, all I care about is the drawing to the right. And I want to write on there exactly where the center of mass is. So I'm going to say paste this on this page. And that's what I've got now. I'm going to get rid of this extra stuff that I copied because I didn't really need that. But what I do need is those values of X center of mass and Y center of mass. So I'll just copy it all as one big thing and then erase it. Well, now I'll just do two separate steps. So I'm going to say copy, and I'm going to say paste. And now I'm going to take this and copy here as well. Copy and paste. So those are my center of mass. Let's remember that we actually used a coordinate system that I can put like this, for instance. Excuse me. So, uh, this is my x-axis, and this down here is my y-axis in the positive direction, downward. So, I'm going to come down here to 28.13, which should be, if you look at this as 60.96. So, if you do 28.13 divided by 60.96, you see that that's just a little under half. So I know the center of mass is going to be a little bit less than halfway. I've drawn the 60.96 as if it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 boxes. So if I go down six, 1, 2, 3, 4, 5, 6, that would be the midway, right about right about here would be midway, and I need to go about 46% of that. So I'm going to say roughly right about, let's say right about here. This is y equals 28.1 centimeters, and that's the y center of mass, somewhere along that line. The X center, actually, I should probably do a little better with that. I think I put it too close to where the Y center, the X center of mass is going to be. So let's write it way out here just to be safe. I'm going to continue this line like that. And now the Y center or the X center of mass will be 8.7529. So if I take 8.7529 and divide it by 40.64, I get that that's about 21%. So that's really only one fifth. The squares here are 1, 2, 3, 4, 5, 6, 7, 8 squares left to right. I want about one fifth of that. Uh, one fifth of that would roughly be right around here, maybe. So this would be XCM is equal to 8.75 centimeters. So our center of mass is roughly there. Notice it's not necessarily part of the body. So what that means is if you, for instance, hung it from something or hanged it from something, then that center of mass would orient itself directly below whatever you hung it from. So you could use a plumb bob to actually mark where that goes through, let's say two or three different spots on the framing square. Then we can hang it from another spot on the framing square. Again, use a plumb bob and mark where it crosses the uh, framing square, and where those two lines run into each other, that will be the center of mass. Again, it will be clearly off the edge, not necessarily, in other words, not necessarily on any part of the body. I drew that a little crooked, so I'm trying to straighten it up a little bit. That works pretty good there. So that's it. I hope that helps you better understand how to solve center of mass problems and how to calculate center of mass. I guess that's it for today. Have a good one. Bye bye.